In this webcast, we're going to see a second example of nucleophilic catalysis, where an aspartate group reacts with the substrate to make a covalent intermediate, promoting the overall substitution where a carbon-chlorine bond is displaced with a hydroxyl group. Haloalkane dehalogenases are the enzymes that promote this reaction, and they've been of interest in bioremediation since these chlorohydrocarbons are quite toxic, where the corresponding alcohols like ethylene glycol are not toxic at all. So what's the mechanism by which these enzymes carry out this reaction? Well, the main step involves an SN2 displacement. We're going to see that the aspartate group on position 124 is perfectly aligned with the sigma star orbital of the substrate, in this case chloroethane. It'll do a displacement on that chloride to make a new carbon-oxygen bond. That's an ester functionality that you can see here. That's the new bond that's formed. It's an ester functionality. The overall reaction involves the displacement of chloride with alcohol. That OH comes from a molecule of water, and so what happens in the next step is a hydrolysis step, and this is where the imidazole of this histidine 289 gets involved. This is going to activate the water by a general base catalyzed process, and it's a small but nonetheless important detail that we're going to use the sp2 hybridized nitrogen on this imidazole ring as the most basic site in the imidazole general base. So we'll activate water as a general base by the imidazole group of histidine 289. That'll end up making the imidazolium cation and a tetrahedral intermediate. That tetrahedral intermediate is now ready to undergo beta elimination, where if we can break that carbon-oxygen bond of the substrate, that molecule which will become ethanol, we'll be able to actually do that if we can do a beta elimination and now use the imidazolium cation as the general acid. So over here, imidazole was a general base. It picked up a proton and was perfectly ready to serve its role as a general acid. The beta elimination looks like this. We've basically made the molecule of ethanol. That's one of our products. And we've got the side chains as the carboxylic acid of the aspartate group, and the imidazole is returned to its neutral form. The general position of equilibrium will lie with the protonation the proton going to the imidazolium group as the imidazolium cation, and the aspartate group as the anion. You can check and see that the overall stoichiometry is balanced. You can also see that the charge is balanced when we consider the chloride, the aspartate group, and the positive charge there, and that negative charge, which is what we had when we began. Basically, to reset the side chain here, this imidazolium group has to return to an imidazole. That's going to happen by a molecule of water will come along and pick up a proton to make hydronium ion, and we'll have reset the enzyme back to its original form. Let's examine that SN2 reaction in closer detail. Basically, there's some key other residues. There's two tryptophan residues that are going to be able to provide hydrogen bond donor groups to the chloride as it begins to undergo the SN2 reaction and develop negative charge. Also, this NH group of the peptide bond on this tryptophan, next to this tryptophan, are going to end up helping to position that oxygen, so it's basically providing rigidity to position that oxygen directly into the sigma star orbital of that carbon-chlorine bond. So if you want to, just go ahead and think about the position of that sigma star orbital as being perfectly aligned with the non-bonding lone pair on that oxygen that's being held in place by these hydrogen bond networks. So as the transition state evolves, we're going to develop negative charge on the chlorine. There's going to be hydrogen bonds that form with those NH groups of the tryptophan, and there'll be a developing negative charge on the chloride and a diminishing negative charge on the aspartate group. That'll undergo complete displacement. The chloride will be now solvated by those hydrogen bonds of the tryptophan residue, and we've made the ester functionality of that aspartate group. Let's take a look at some pictures. The haloalkane dehalogenase from this view you can see is one of those alpha-beta open twisted sheets, and if you looked carefully you'd notice that at the position in this region, actually that's the chloride atom right there that I'm pointing to in green, here's where that crevice forms in that alpha-beta open twisted sheet where we recognize the enzyme active site. This is just a couple of pictures of showing you the size of the enzyme in both space filling and then in a rendition of a cartoon or a ribbon diagram. Here you can see the enzyme active site. The chloride atom is shown in green, and what we're going to do now is zoom in and look at where those active site side chains are. So you can see the histidine group there, the histidine, there's the tryptophan, that's the aspartate group, and there's the chloride atom that's already been displaced in the enzyme active site. And finally, one last view where we zoom in and take a look at the position of those side chains. So here's the aspartate group, and it's connected with as an ester to the dichloroethane molecule, and over here you can see the tryptophan that's going to hydrogen bond to the chloride atom there. There's the tryptophan that's positioned with its NH into the chloride anion that can be solvated.